Everyone, welcome to the Energy Efficiency in Buildings session of this conference. I'm Dave Jenkins from Heriot-Watt University. I'm the theme leader for Energy Efficiency in Buildings in ETP. So for this session, we've got 4 speakers, and we heard earlier from Chris Stark about the importance of energy efficiency in buildings, and perhaps putting a bit of pressure on our speakers to come up with some interesting and innovative ideas to try and deal with this really significant challenge we have to make our buildings more efficient. So 4 speakers, 15 minutes each. If I can ask all speakers to keep to time as best as you can, I will pop if you start going over time. There'll also be a few minutes of questions at the end of each presentation. If I can ask everyone in the session to put in their questions into the discussion forum, and we'll try and pick up as many of those questions as we can at the end of each presentation. So our first speaker is Bohan from Heriot-Watt University, and they're going to talk about using cardboard box to buffer temperatures and humidity fluctuations for preventative conservation. So I shall pass over to Bo.
Yeah, thank you, David. Hello, everyone. I'm Bohan, a PhD student from Heriot-Watt University. Today, the most important thing I want to share with you is a passive measure in preventive conservation using cardboard box to buffer temperature and humidity fluctuation. And in my research project, this is the experimental part to prove the feasibility of considering passive measure for energy saving control. To prove the feasibility, my presentation will provide relevant evidence from the experiment. There are 4 parts. Number 1, introduction. Number 2, experimental aim. Number 3, method and equipment. Number 4, preliminary findings. Let's start the introduction now. From the perspective of collections care, the library's collections like the babies, they need to be cared in an appropriate environment to avoid any detrimental effect. Now, the National Libraries use HVAC system to provide appropriate environment with tight control for whole storage room. However, when the collections are enclosed in the cardboard box, the box like the baby's incubator, so the collections are shielded from atmospheric influence of the storage room. Yeah, they should be quite comfortable stay inside. And present environmental control in the National Library focus on the space of whole room. For most paper-based collections in the National Library, the control bands of temperature and RH are 50 to 25 centigrade with 5 centigrade 24-hour fluctuation and 40% to 60% RH with 10% 24-hour fluctuation. When we compare the outdoor temperature and RH in Edinburgh with the control bands, we can find that the heating and dehumidifying are necessary for most of the time. So the HVAC system has to continuously work to make stable temperature and RH within the control band. It leads to much energy consumption for 24-hour multiplied 365 days. From the perspective of energy saving, I always associate the box with the passive house in my brain. Although they are in different scale, there are many common points, especially for their envelopes. The box envelope consists of several layers with various functions. For example, the gray surface contains polypropylene. The polypropylene can sufficiently avoid water damage. And the second layer is made of a cotton pulp. It can provide heat insulation. And the inner layer with absorbent material can help to adjust RH fluctuation in the small space of the box. The design of passive house can provide comfortable space and consume little energy in the field of passive house. How about the cardboard box in the field of preventive conservation? Because most collections are housed inside cardboard box for preventive conservation, the cardboard can absorb and release heat and moisture from surrounding air to shape the peak of temperature and RH fluctuations due to its hygrothermal properties. We believe that hygrothermal buffering effect can provide actual protection for the collections. So under required temperature and RH fluctuation in the standards, the environment inside the box is more stable than the room because the environmental control usually focuses on whole room. It means that accuracy of control is higher than the standard when the box environment is regarded as controlled space. For present environmental control, it is time and energy consuming in the National Library. So we want to guarantee that the temperature and RH inside the box are controlled within the control bands rather than whole room. Further, the accuracy of environmental control in the room can be relaxed to save energy. The low accuracy of control can help to achieve low energy consumption. Therefore, this experiment aims to measure and quantify the buffering effect for proving the feasibility of the relaxed environment room control. Besides, there are 5 basic principles in the field of passive house. Compared with these principles, thermal insulation of the box, yes. Airtight, yes. Optimized window, no need for the box. Balanced ventilation, yes. No thermal bridge, yes. So based on the theory of passive house, our box is possible to provide appropriate environment for preventive conservation and consume little energy. And to prove our feasible idea, there are 5 steps for this job. Number 1, we need to define some variables to quantify the degree of buffering effect. Number 2, considering the on-site situation in the National Library, there are 2 parts for testing. The focus of part 1 is to check the difference of buffering effect in different placement form among the same dimension boxes. And based on the best placement form, part 2 focuses on checking the buffering effect under different temperature and RH fluctuations. And then arrange the testing procedure. It includes temperature and RH logger calibration, logger placement, acclimatization, and simulation of temperature and RH fluctuation in a hygrothermal chamber. The simulation is set for the same amplitude of fluctuation, but in different period of time. The amplitude of fluctuation is same, but the period of time is different. And finally, analyze data to obtain findings. In detail, the following new variables were devised. Number 1, temperature fluctuation. It is an average value to describe the difference between the maximum and minimum temperature in the period of harmonic oscillation. The harmonic oscillation means the fluctuation with same amplitude in a same specific period, like the figure 1 shows. I is the number of cycle period. The maximum temperature is the value on the peak, and minimum temperature is the value in the trough. And the peak and trough are searching according to the derivative calculation. When the value equals to 0, they are the peak or trough. It's easy to understand, right? And number 2 is RH fluctuation. The logic is same with the temperature fluctuation. Number 3 is temperature buffering, because the box envelope can store and release the thermal energy to moderate the fluctuation from the room. The temperature fluctuation inside the box is smaller than the room. Like the figure 2 shows, we use absolute different temperature buffering to indicate how much fluctuation is moderated. Number 4 is humidity buffering. The logic is same with temperature buffering, using the fluctuation in the chamber minus the fluctuation in the box. Number 5, the amplitude ratio of temperature and RH. They are used to indicate the relative magnitude of the fluctuation between chamber and box. And the final one is a coefficient used to describe what's the exposed area of heat and mass transfer for per volume of the box. The smaller shape coefficient, the less heat and mass transfer between chamber and box. For the method and equipment, a plenum chamber was used to test the buffering effect in different shape coefficients of the boxes. The temperature and RH was set at 25 centigrade and 55% RH. In this setting, the daily temperature and RH fluctuation for the chamber are similar with the National Library storage room, 1 centigrade and 4% RH. Meanwhile, the boxes were placed in 3 different forms, like the figure shows, and all boxes are empty inside. And to test the buffering effect under different temperature and RH fluctuations, a hygrothermal chamber was used to simulate the room environment with specific fluctuations. The fluctuations focus on 5 centigrade per 10 minute to 90 minute and 10% RH per 10 minute to 300 minute. Moreover, to simulate the different volume of paper-based collections filled inside the box, 5 same-dimension boxes were filled with 0%, 30, 50, 70, and 100% newspaper inside. In the preliminary findings for the part 1, we can see the shape coefficients of same-dimension boxes in the table. The difference of values are quite small, right? But actually, although the value of shape coefficient looks similar, their exposed area are quite different in the scale of box. I need to explain something here because the shape coefficient is a variable used in the field of buildings. The box dimension is quite different with the building. And I just borrowed the measure directory. That's why the coefficient looks similar here. However, I didn't find a better variable to indicate this feature now. If you have any good idea, please share with me, and thank you very much. And for the result, when the plenum chamber was set at 25 centigrade and 55% RH, after 48-hour test, the results showed that the temperature and humidity buffering and amplitude ratios are almost same among the same dimension boxes. So the placement form did not affect the buffering effect. That is not the best form for buffering effect here. And from this perspective, the placement form is not critical in National Library. And meanwhile, we also can select one suitable placement form for the test under different temperature and RH fluctuation. And for the test of buffering effect under different fluctuations, it includes temperature buffering and humidity buffering. Regarding the temperature buffering, the hygrothermal chamber was set in 70 to 22 centigrade fluctuation and fixed 50% RH with 10 minute to 90 minute period of time. Because the RH was fixed at 50%, the chamber cannot control temperature fluctuation ideally for 10 minutes and 20 minutes due to the limitation of the chamber control. Yeah, but they are also show that the box temperature fluctuation is about 3 centigrade smaller than the room. And other results show that number 1, there is 0.5 to 2.15 temperature buffering for the relaxed room environmental control. Number 2, with the decrease of temperature change rate, the temperature buffering effect also decreased significantly. When the temperature change rate is lower than 5 centigrade per 90 minutes, the heat transfer will reach a relevant steady state. In this situation, the box temperature fluctuation is almost same with the room. Number 3, when the temperature change rate is too large, larger than 5 centigrade per 20 minutes, there is a risk that leads to RH inside the box out of the control band. The RH will lower than 40%, and 40% RH is the lower limit in the standard. Regarding the humidity buffering, the chamber was set in 50% to 60% RH fluctuation and fixed 20 centigrade with 10 minute to 300 minute period of time. Same with the test of temperature buffering, the RH was not controlled well for 10 minutes and 20 minutes. Although these two groups of data cannot be used to compare with others, their result also show that the box can moderate the RH fluctuation from the room. And for 10% RH fluctuation during 30 minutes to 300 minutes, there are 4.75 to 8.75 humidity buffering for the relaxed control. It means that the RH fluctuation inside the box is about 4% to 8% RH, smaller than the room. Meanwhile, with the decrease of RH change rate, the humidity buffering effect also drops. However, compared with the threshold of steady state of heat transfer, the threshold of moisture transfer occurred in the quite small humidity change rate. So considering present tight control in National Library, they control the change rate is quite small. For daily control, it's almost 0 or 1 centigrade, and the RH is close to 2 or 4% RH. So the box ability of shifting RH fluctuation is more potential for contributing to relaxed room environment control in this step. And finally, I want to say the experiment proved that the box can provide enough buffering effect for relaxing present accuracy of room environmental control in National Library. Now the room temperature and RH are controlled within 1 centigrade and 4% RH for daily fluctuation. It is too tight. And to save energy for the constant temperature and humidity air conditioning system, in theory, the possible fluctuation can be relaxed to 5 centigrade and 10% RH per 30 minutes when the passive measure was taken into consideration. Of course, the set point should be set at the middle of the control band for this situation. However, the set points also affect the energy consumption. So my further study will base on the passive measure to determine appropriate temperature and RH for the National Library's energy saving control to save to reduce carbon dioxide. Thanks for your listening. And if you are also interested in the study of passive house for the collections or energy saving control for the constant temperature and humidity air conditioning system, please contact with me. My email is bohan36@harrywatch.ac.uk. Thank you very much.
Thanks, Bo, and that was bang on time as well. So thanks for keeping it tight. We've got one question in the discussion forum from Antoine. So are you looking at lifespan of the box and how many cycles the box could handle with similar performances?
You mean the cycles? Usually I will do about 10 to 20 cycles, the harmonic oscillation. I will use
so I think the question is around, are you able to kind of relate that to an actual lifespan that the box could last for based on number of cycles?
Oh, yeah. Actually, my research focused on the buffering effect. For the cycles, I didn't carry on this study until now. Yeah. And this is a good question I will consider and do. Yeah.
I've got one question just on the, so you looked at different sort of aspect ratios of boxes. Is there any way you can extrapolate your findings for larger shapes? Because obviously as the shape gets much larger, the surface area to volume ratio gets less, and so the buffering effect will potentially reduce. So is there any way you can extrapolate the findings of your very small shapes to much larger shapes, or do you just need to do more testing?
Yeah, but actually, the National Library has the standard for their box. So, and in this step, I just use the standard boxes for the test. Yeah.
Okay. I have another question from Leslie. You mentioned that energy savings could be achieved. Do you have an estimate of how that could compare to current energy usage?
Sorry. Compare.
So are you able to relate kind of quantified energy savings to typical energy usage?
Yes, actually, this is this is my next plan, because the HVAC system is different with the common one, the comfort AC. This is the constant temperature and humidity control. That means the temperature and IH will be very stable for whole week or whole days. So the control logic is very complex. Next step, I plan to use MATLAB simulation to model this kind of equipment. Every component of the HVAC system, and I will use turning the PID to control this system and to check, for example, under 1 centigrade accuracy, control accuracy, and corresponding to how much energy will be consumed. Yeah. Okay. This is a very different type of HVAC system, compared with others. So also, when we do the simulation for energy consumption, it is also totally, different.
Yeah. Okay.
That's
great. Thanks very much, and thanks. Yeah. Thanks for your presentation. That was great. Okay, so our next speaker coming up is you a little bit. Olufalaki is from Glasgow School of Art, and they're going to talk about a systematic review of research studies on carbon footprint and user satisfaction in housing in Lagos, in Nigeria. So Olufalaki, over to you.
Thank you very much. Can you hear me?
Yeah, we can hear you. Just wait for your slides to come up.
Okay, I'm just going to get my window up. Yeah. Yes. Can you see me? Sorry? Okay. Hi, everyone. My name is Olufalaki Olumogwa, and I am a final year student, PhD, Glasgow School of Art. My topic for this ETP conference is a systematic review of research studies on carbon footprint and housing satisfaction in Lagos, Nigeria. My PhD currently has is to do with, well, it is a bit related, and it's been quite good doing this review because then it sort of brought the whole thing into a better perspective, what I'm actually doing. This is an artist's impression of Lagos, Nigeria. Lagos, Nigeria is coastal, and there's a lot of shanty settlements along the coast, made from timber, which timber is very it's a good material for carbon sink. And so I just look at the picture and I think it's an artist's impression. There was something similar that was actually piloted using reusable plastic bottles, but containers. But I mean, it didn't stay up for too long. But I believe it was a pilot. You know, we're learning a lot from it. But anyway, how I wish we can get to this one day. Okay. Basically, I'm going to talk about Lagos very quickly. A background. Lagos has a population of, I think, 14.23 million in the city of Lagos area. And if you include the environment of Lagos, it's about 20 million. So it is one of the fastest growing mega cities, certainly in Africa, probably in the world. The picture on the left shows Lagos as it is today. I think this picture is probably asking super city, but it's fairly, that's the island. It's made up of several islands, as you can see from the map location below. And there's a new reclaimed area called Eco Atlantic City, which is new. And this is typical of mega cities that sort of expand oceanwards, towards the coast. I can't say, I mean, there's a lot of engineering going into making sure everything works out well. But that's, I'm not in the position to really It's not something I would, I don't know. I'm not an engineer, but it's working. It's worked before, and it's happening at the moment. And actually, the other islands around Lagos have been reclaimed historically, even though the coast has been eroded, which is part of the problems of climate change. Lagos is the biggest largest port in Africa. There's a housing deficit of about 5 million in Lagos. It's a paradigmatic self-regulating city. It's dysfunctional, it's disconnected, it's informal, but it works because people, it's just a different model completely. Lagos accounts for about 70% of industrial investments, 90% of foreign trade flow, 60% of energy consumption, and over 30% of Nigeria's gross.
Hello, Iman. I can hear you nice and clear now.
Lagos.
Yes, I can, yes.
Dwellers live in slum, and it's the second most expensive state market.
I am
Most people in Lagos are living
not 100% sure.
On less than $1 a day.
So you don't have any applications that you can close in your browser?
This paper is a systematic review examining.
My opinion is that it's going to work.
The relationship between carbon footprint.
In my opinion, this is going to work the next time you are in the preview.
Being one of the
because I'm getting sound, and maybe for some reason we lost the handshake digitally, but because we are getting it now in the platform.
The subject of my PhD thesis, which is nearing completion. It's a review article on the findings of various authors of the assessment of how carbon footprint affects user satisfaction in selected housing types and how to facilitate low carbon living in the global south. This examines mass or affordable housing, 2 to 3 bedroom units.
No, sorry.
This
so you can only hear me if you have the room.
Due to income disparities within the coastal megacities. It is a qualitative assessment of the findings of the effects of carbon living on selected households, comparing assessments from similar urban locations, while including select parameters to streamline the study within an epistemological built environment and architectural perspective, to propose a guide for a regulatory framework for urban density, carbon emissions, in housing satisfaction and sustainability, and to facilitate low carbon living and user satisfaction towards zero carbon in cities of the global south. The selection process I'm using for my study is using the SPIDER tool, which is a sample, which is different from the PIC, which is more familiar. It's used a lot in health studies and comparisons. And I would later on talk about why I am using the SPIDER tool. Actually, some various articles of the topics from e-journals were selected from databases using a 3-man review team with inclusion and exclusion of the process only. This selection strategy includes the population type, unit size, durations, period of the written review, i.e. in the last 10 years, location, carbon emissions, housing use, embodied carbon in buildings, exclusion factors as low density units, and life cycle.
So my idea is Catherine could hear me, but the presenter is not.
I'm going to go to the next slide. And basically, this explains the distribution of carbon global emission sources. As we said repeatedly in this conference, buildings have a lot of carbon, contribute to carbon emissions. And in my pie chart, I've got electricity, heat, aviation, shipping, cement, iron and steel, combined heating and electricity, residential and commercial, load following electricity, other industry. And it's been apportioned the different percentages. Basically, carbon energy use and carbon intensity are indices of the environmental sustainability of buildings, and they contribute to global warming and ultimately climate change. This study literature is a review of what exists as carbon footprint, emissions related to housing, and user satisfaction in relating to this footprint. While there is a growing literature based surrounding carbon emissions and user housing and resident satisfaction to date, there has been no systematic scholarly review of this phenomena with reference to Lagos, Nigeria. Systematic reviews are rare and can be described as producing a deep understanding of various studies and assessments in that area. Available study has been on a case study basis. The study area of Lagos, which accounts for 70% of industrial investment and foreign flow, Lagos has an influence, a geographical because of the coast, and so it has the attendant challenges and difficulties of a megacity. I've got below two graphs showing it's like a proposal, a projection from 1970 to 2030, and if you follow carbon emissions in Africa, it's pretty low. I believe it's in it's like light pink at the bottom. So typically the continent of Africa really has very low carbon emissions. But to my mind immediately, my suggestion would be sort of carbon capture and all the likes of that. So just very moving forward, I'm going to talk about my sample selection. I sampled 7,109 articles across various databases. Initially, I deselected the database, the journals based on environmental studies, architecture, and urban design, and it resulted in 120 articles, and I read all the abstracts, and I just deselected the contents to be relevant to carbon footprint or emissions in housing or user satisfaction. And then I got 90 articles. I then invited 3 interviewers to read abstracts and select based on priority themes. Eventually selected 4 articles, and I read the articles and synthesized them for the purpose of this presentation. I'm going to talk about the spider tool, which I used for my selection. The spider tool is different from the PICO, which is typical. So probably more familiar for systematic reviews. And what you have the sample, the phenomena of interest, design, elevation, and research tab. It's typically used when you are comparing, or rather it was designed to be used articles are not quantitative, they're more qualitative in nature, and that's why I have selected this tool, particularly because it's like an assessment and a comparison of what exists in Lagos, Nigeria, and other similar places or other literature relevant to the topic. So it's somewhat different, and the 4 primary themes which I selected were the effects of carbon emissions, carbon footprint in housing. That's CO2 measures, carbon dioxide measures, air quality, building density, and embodied carbon. So those were papers that included those type of themes. Then the next priori theme was connecting energy use and energy and carbon emissions to user and housing satisfaction. And the themes came up with daylight, ventilation, fuel appliance use, privacy, socio-economic factors, neighborhood and environmental satisfaction. The third theme was sustainable outcomes of nearly zero energy buildings. Our recommendations and actions were the areas I sort of focused on. And the last one was carbon emission, carbon footprint in urban forms in global south. So I looked at cities like India, Brazil, Puerto Rico, any article in Malaysia, Kuala Lumpur, any article that related to those topics and were relevant to what I was trying to achieve. In considering user satisfaction, I looked at the Maslow's needs theory, which very interesting is psychology, safety, love, belonging, esteem, and self-esteem, self-actualization, sorry, as themes in determining user satisfaction. And I've got a pyramid on the screen here, and I've got the components of residential satisfaction as social demographic characteristics, demographics of residents, socioeconomics of residents. And this includes age, gender, marital status, income, duration of residence, tenure, race, education, household size, job status. I looked at the housing and auxiliary characteristics of physical characteristics, support services, management factors, building quality, features, and this will number of rooms and sockets, size of rooms, dining, kitchen and living areas, dry area, quality of house, toilet, bathrooms, ventilation, parking, corridors, staircase, etc. So really the building itself, which I discovered that really was the area of focus when it came to emissions and carbon footprint, which I would prefer to focus on anyway, because in Nigeria the like, you know, power use is very epileptic and not very reliable. I mean, you get grid electricity for 1 to 5 hours daily. It's improved possibly in the last 2 or 3 years, but because government has tried to decentralize power and has encouraged private participation, but they still have a long way to go in sorting that out. As part of user satisfaction or resident satisfaction is neighborhood characteristics, neighborhood facilities, social environment, public facilities, access, safety, security, infrastructure, privacy, urban activity and noise, neighbors and relationships, access to be able to get to and from work, income-related behaviors, and behavioral characteristics as the residents' behavior towards the residents, the mobility, modification, adjustment, adaptation, maintenance of culture. It's been quite interesting.
A warning there, so 30 seconds to a minute left, if you could begin to wrap up.
Okay. My design rationale is more like the house. I'm looking at this slide shows all the features that embody carbon. This is a list of articles I selected, and these is how I reviewed them. And I think I'll just go very quickly to the end of sort of, this is my case study area, and you've got all the power poles and all the self-help electricity they provide for themselves. Last year, then, to talk about my research findings, the recommendations. But finally, this is India, where it could be Lagos. So it's a good thing as looking at things like that. But I'll go to the recommendations for future research. I think everyone's said it here, of carbon capture and carbon offsetting, but I think I would recommend a pilot scheme to see how reusable energy in RET, that's renewable energy, and also building materials and design should be looked into to be able to achieve the carbon, meet the goals of COP26. It's going to take a long time, and I think anything else I'm saying has actually already been said. And so I hope I'm within the time limit. Well, thank you so much for giving me the opportunity to speak here. There are lots of research gaps, and just, you know, life cycle assessment, indoor environment quality, end user behaviors. We've got smart grids, optimal design and retrofit, renewable energy sources, nearly zero energy buildings, which could really be achieved. And I think using wood as opposed to concrete, which is used mainly in that part of the world, would really be an innovative way to achieve a lot of these goals.
Okay, that's great. Thanks very much for that presentation, Olufalaki. We have a question in the forum from Antoine. So why a decentralized electricity system, or why can a decentralized electricity system provide a better supply than a centralized one? So why would your, I guess, default position be to favor that?
Well, actually, right now, what government has done is they've sort of privatized electricity. They've got what they call discos for distribution to the end users. But the actual generation it hasn't been decentralized at all, because there's just so much bureaucracy. There's so much sort of paperwork they have to get through, and I think a lot of political interest as well, which is one of the challenges we face in that part of the world, of people having interests and not actually doing what they're meant to do. I don't know if I'm supposed to be saying this here, but that's the reality. I don't know if I've answered the question. So they have started, but it needs legislation in place. For example, if you have a pilot scheme or a small scheme that can actually produce and generate their own renewable energy, because you can get solar energy, you can get wind energy, you can get energy from the ocean, especially as Lagos is by the ocean. There's just so many source energies, and I think that really would have to be the way forward eventually. And it has started, slow though, but it has started.
Okay, I've got one question. If there's no other questions coming in, I don't know if I missed it. Are you able to expand on your user satisfaction part of the work? So what is the methodology, the process to actually understand and gauge user satisfaction in the target areas?
Yes, no, I wasn't able to because I time was against me. But basically, to engage one is a participatory approach even in the work I'm doing. Two is introducing. I mean, if I look at what exists here, like you have smart grids, they have actually started installing smart grids now, the private discos, and so being able to. Technology is so far from that, but what we can do is in design, in the type of materials. For example, the traditional materials are actually carbon efficient. I call it carbon. So if you consider clay as opposed to concrete, and earth as opposed to steel, and wood, and so there needs to be like sort of education and encouragement and in actually getting people to understand. So it besides what we're saying here, but what we do, we talk to them and tell them, or this encourage them and at the level of the user level, and ask. I think really basically the interview or the research would actually point in the direction of what would be the best way they are satisfied. I know from my review that once what they want is there, they are satisfied. They own the home and the features they want in it. But we're looking at, carbon. How do we? I mean, it's not a big thing, but it would help in reducing costs.
Okay, we do have a couple of other questions if we can just answer them really quickly, because we are a bit short of time. So a question from Leslie, are you considering all types of housing, first of all? So obviously your solutions are different for high-rise buildings compared to lower quality buildings. So are you looking at all types of housing, first of all?
Well, for my study, no. But in this review, I've actually looked at high-rise buildings as well. I have just because someone's already looked at it, and yes, I mean high-rise buildings do have a lot of carbon, embodied carbon, and so. But I'm not in my research. I'm just starting from embodied carbon on site, as opposed to bringing it to the site, because there's a lot of carbon involved in taking it to the site.
Okay, so, and again, just sorry, just because we're a bit short of time, just really quickly, another question from Johnson. Based on your findings, what do you think is the primary cause of, I presume that variable interrupted power supply in Lagos in Nigeria?
I think the systems need overhauling. Okay, it's running a lot of fossil fuel. It's centralized and it should be decentralized. I think that's a way forward globally now. And that when it's decentralized, it's more control. You've got issues of it, traveling miles to get to those who need it. You've got maintenance issues. You've got just all sorts of things. So decentralizing would be a better solution. And they are trying to get there, but there's a lot of bottlenecks. So that's a lot of problems. Are they obsolete? The equipment's are obsolete. They need a lot of training. It needs a lot of
a multifaceted problem with many issues. Okay, thanks very much for your presentation, Olufalaki. That was really interesting. We're now going to try to get back to Iman again.
Hello, David. Hopefully, can you hear me now?
Yes, we can hear you. That's a good start. Good. So Iman Maya is from Glasgow School of Art. And as I said earlier, you're going to be presenting about long-term monitoring of daylighting and potential energy saving in design studios in Scotland. So Iman, hopefully over to you.
Okay. Hi, David and everyone. Just checking if everything is fine, if everything's stable.
All looks good at the moment, yeah.
Okay. My name is Iman Maya. I'm a PhD graduate from Mackenzie School of Architecture. I will present part of my PhD thesis that's supervised by Dr. Rad Hanna and Professor Tim Sharp. This research is dealing with long-term monitoring of daylighting and potential energy saving in design studios in Scotland. As we know that daylight is fundamental in architecture for creating sustainable and healthy living environment. It's also a crucial parameter in sustainable energy research. It reduces the need for artificial light and plays a key role in minimizing HVAC costs. Previous research has found that daylight can save up to 77% of the energy used for lighting. However, in overcast locations such as Scotland, designing to ensure sufficient quality and quantity building is challenging due to climate conditions, including high cloud coverage, synonymous with dark and gloomy sky conditions and sunlight availability, like the position of the sun, solar elevation angle, and sunlight hours. Decisions on facade fenestration design and the use of artificial lighting are mostly geared towards providing sufficient interior illuminance without addressing the crucial influence of facade fenestration in daylighting and energy efficiency. This study aims to assess daylight performance with various facade fenestration of design studios in 3 Scottish cities, Glasgow, Edinburgh, and Aberdeen, and its potential to reduce use of artificial lighting. As the study orientation is crucial in daylight availability, the study was conducted in 2 stages, depends mainly on the north and south orientations. Daylight measurements were carried out simultaneously in studios with north orientation from Glasgow and Edinburgh, followed by simultaneous recordings in studios facing south from Glasgow and Aberdeen. The study methodology is empirical with long-term monitoring of luminance levels conducted inside and outside of the investigated studios. A longitudinal research design was adopted for this study. Therefore, the research methodology is largely experimental. It involves quantitative data measurements, namely facade fenestration, daylighting levels, and distribution inside the design studios. As the study mainly deals with the measurement of daylight levels, the location of the case studies in terms of their geographical coordination, sun altitude, season, and time were all crucial to consider. To clarify, the build altitude determines the solar elevation, solar radiation, length of daytime at different times of the day, and also different season of the year. Therefore, the outdoor illuminance is highly affected by the latitude of a building site. When considering their latitude and longitude coordination, there is no time zone difference, meaning that the cases have similar values of sun altitude, direction, and length of day throughout the year. As such, the parameters that are related to the sun's effect on daylighting performance at specific areas are roughly similar, such as sun altitude, direction, daily total sunshine, and global radiation. The climatic conditions of a site also define the overall daylighting performance in a building. Within this research, cloud coverage in octas, daily total sunshine, and daily total global radiation were checked hourly for the 3 cities during the which was from February to October 2019, just before the pandemic. Using SPSS statistics program, the hourly cloud coverage descriptive data for the 3 cities was compared to check if there was a notable difference. In terms of cloud coverage frequencies, all cities have 8 octaves of cloud coverage, which means overcast, sky completely cloudy, as the most frequent amount of cloud coverage throughout the study period, with Edinburgh registering 42.8%, Glasgow 43%, and Aberdeen registered 48.4%. In comparison, the clear sky with 0 octaves of cloud coverage for Edinburgh registered 15.8%, Glasgow registered 16.5%, and Aberdeen registered 12.7% throughout the study period. So ultimately, there is not a notable difference in the climatic parameters that affect the daylighting performance between the three cities are overcast. The average external luminous levels measured under unobstructed sky for the 3 cities. The findings show that the maximum luminous level registered in June, while the minimum luminous level registered in February. The external luminous levels were important to measure also for the daylight factor. The investigated studios have different typologies, which I will present 4 types of them. The light meters have been placed from the window wall to the back of the studio horizontally and vertically. The daylight levels inside the space can be presented in an absolute value as the illumination level at a reference point. Accordingly, the performance of daylight inside building is often characterized and controlled by standard codes of practice and building regulations. Were introduced to ensure the safety of people in terms of visual comfort and task performance purposes. As the task luminous requirement for both daylight and electric lighting are the same, this study has relied on guidelines relating to the art rooms in art schools when evaluating the luminance levels inside the investigated studios, in which the recommended luminance levels are between 500 to 750 lux. So this studio is north-orientated, double volume, and has high window sill height with no outside obstructions. Even though there was a high cloud coverage, the meters registered daylight luminous levels of more than 500 lux in taken from February to October. Indicates great potential for saving energy used for lighting with window to wall area ratio 84%. However, the presence of a mezzanine reduced the registered luminous levels of less than 500 lux, and so the artificial lightings were switched on all the time during the day. Had totally different values due to the window placed in line with the studio, yet due to the outside obstructions, either because of buildings or trees, luminous levels registered less than 500 lux in some of months such as in February, March, April, May, September, and October, and particularly in reference point in the back of studio. This studio is also double volume with mezzanine above. There is also outside, but the window around the studio, and so the mezzanine prevented from efficient daylight. Here, and in contrary with the previous cases, the luminous levels registered less than 500 lux in most of months, which indicate and confirm that vertical windows with high window sill height are sufficient for overcast locations. However, the need to provide outside view is still an outgoing argument between architects and educational thinkers. This is the mezzanine studio that highly rely on artificial lighting to provide the for south-orientated studios, and particularly for the ones with skylight, the luminous level registered more than 500 lux in May, June, July, and August. but studios with no skylights, illuminance levels registered less than studios with a skylight. Of course, skylight plays an important role in providing sufficient illuminance levels, especially if it's orientated to the north to prevent the problem of glare. Finally, data related to the energy consumptions for only artificial lightings were not available. Energy consumption in most of cases were about the electricity consumption as a total, and for the entire building rather for each studio. So that's take me to summarize that as the energy efficiency is a straight path towards energy sustainability, and despite the significant advances, the policies should be improved to adopt and produce to promote sustainable development. And although the Society of Light and Lighting present code that recommended the maintained illuminance surface for the educational building, and the British standards recommended the daylight provision by daylight openings, there are still no suggestions or recommendations that relate to creative spaces in educational buildings, and here such as as an architecture and design studio. This issue drawing attention to how the theory and typology of creative are still under development. The window characteristics, along with the studio typologies, are crucial to in the early stages of design, not just for functional needs and human comfort, but also for energy efficiency. Furthermore, weather considerations and the presence of outside obstructions such as buildings and trees force to consider an integrated system of both daylight and artificial light. Subject the user's experiences inside spaces should be present and evaluated for different approaches of energy sustainability. And here I remember one of the students commented that she was doing her work in a studio oriented to the north, but she comments that artificial lights were switched on most of the time. So I checked the light meter and it registered more than 500 lux. So when I asked her, said that the nature, the color of daylight is more gray, and they need orange or yellow, like for more experience and atmosphere. So they tend to turn on the artificial lights, even there is a good daylight. And for the studios oriented to the south, students also still tend to cover the windows with curtains to prevent from glare or direct sunlight hits their screen. And one of the students also told me that he used to wear sunglasses inside the studio because of the direct sunlight most of the time. So subjective concerns are very, very important, along with the objective measurements. That's it. Thank you very much for having me.
Thanks very much. No questions coming into the discussion forum. So in the meantime, I've got a question about the measurements. So you're either measuring kind of point illuminance or sort of average illuminance across an area. Are you also recording the distribution of illuminance? Because obviously if you're speaking to people using those spaces, then it's not just the lighting level on average, but it's the distribution of illuminance is really important to provide a good visual environment. So are you able to also gauge that as well? Because obviously if people are dissatisfied with those areas, it might not be the lighting level in terms of magnitude, it might be the variation over that space.
Yeah, there were many measuring points spread for the total area of the studio. Actually, there is an equation to use to decide how many measuring points should be inside the space, but because this investigation was in real life and real circumstances, so before I located the light meters, I had to spend way long time discussion with the tutors and the students if the light meters location are fine with them and they don't distribute their work or their environment. So I like at least 10 to 12 measuring points were put in each studio and in very specific locations to have clear and comprehensive daylight distribution inside the studio. Yeah.
Okay. Yeah. Many years ago, I did something similar, and I know how difficult it is to actually measure light in spaces that are used. You kind of want everyone to leave the room, but that's not usually possible. A question just come in from Leslie. Did you consider thermal comfort versus lighting level? So, for example, more windows provide more light, but could result in more heat loss or drafts.
Actually, I've measured temperature and humidity, but for this particular work, I have a certain aims and goals, so I didn't include anything about thermal comfort. But I'm very, very, very interested to check the data again and see if there's any correlation. And of course, I would say yes. Of course, especially in the South-oriented studios, the students give me very, very strong comments and recommendations on how to design and where to put the window, what should be done, which was fascinating for me as a researcher.
Mm-hmm. Good. Okay. Thanks very much for that, Iman. No other questions. I think we're just about on time. So, final speaker before we break for lunch is Antoine Rigius from Edinburgh Napier University, and he's going to be talking about connecting Scottish public buildings to low temperature heat. So over to you, Antoine.
Okay, thank you. I guess my mic is open now, so you can hear me properly. So yes, so that's my PhD. This PhD is funded by ETP, and I've got an industry partner who is Vattenfall. Vattenfall is already very here in Scotland for wind farm, but district heating, that's something new for them. And Edinburgh, the city of Edinburgh Council, is also a partner for this PhD. So I'll be quick on that because I'm focusing on decarbonization of heat, as that has been described by Chris Stark earlier today. And we go for, so we have to decarbonize heat. Just now we are relying on gas. 2050, 2045 for Scotland, we have for non-domestic buildings, we have to rely on heat pumps and low carbon heat networks, which will be supplied by large-scale heat pumps. And the key challenge is both technologies, heat pump and district heating, they are much more efficient if they operate at reduced operating temperatures. So our buildings are usually designed for 80 degrees. Can we drop the temperature? Questions. There's a question about the domestic hot water. We can't go too low. Under 60 degrees, we would have a problem with Legionella and so safety of hot water. And below that, we have 50 degrees, which is the minimum temperature we have to reach for tap. So for domestic hot water and for space heating, the current standard in the UK is to operate at 80-70, so 80 degree flow, 70 degrees return. And the new aim, or the new standard, which is developed mainly in Scandinavian countries, so Sweden, Denmark, so district heating, the new generation is to operate between 55 and 25. So that's quite a drop from the current standards in the UK. So the PhD is, can we connect public buildings to low temperature heat and fourth generation of district heating? The driver is we have to look at public buildings because public buildings and local authority are first in line, because if they are connected first on the district heating, it's a very good way to de-risk a project, because the heat supplier will be able to know there will be a heat demand and large heat demand with schools, offices, etc. And also my driver for the PhD is for the asset manager, for local authorities to plan ahead and say, is my building low temperature ready? So if it's sort of green light, yes, we go. Orange, we have to change radiators, or red, we have to retrofit the envelope. And that can be done ahead of the connection. So the methodology is first to do a literature review, what has been done abroad, and the rest would be, or the methodology would be to a characterization of Scottish public buildings. How do they perform, and can they connect to low temperature heat? One point will be to evaluate the oversizing of space heating systems, and I will finish with a case study on Borders College in Cadachilles. So the literature review is finished. That has been published 2 months ago, and the main outcomes are as follow. So low temperature heat is something new even in Denmark and Sweden, which are countries where district heating is very well developed. And the main idea there is there's a nascent readiness in Denmark. And if a building is not ready to connect to low temperature heat, a little bit of oversizing of the heating system, space heating system, is sufficient to connect. So that's very encouraging for that kind of for those countries. And when it is not possible to connect, most of the time it's not because the system is not able, it is because there is faults or errors or malfunctions in the system somewhere, and that usually can be easily fixed. So the key question is, can we export Scandinavian conclusion into the UK? So in the UK, space heating is likely to be significant. It could be 50%, 100%, and sometimes up to 400%. So if we compare to lessons from Denmark, that would be sufficient. But there is limited publication focusing on the UK. In the UK, the systems are operating at higher temperature. So the step is higher if we want to drop it, to reduce it. And we operate our systems with a small temperature drop across radiators, which is an issue for district heating because they need a low return. In the UK, we connect our radiators with bottom entry, bottom exit, while the standard would be to have a top bottom. And that reduces the output of radiator by 5 to 15%. So that's something that we may have to change. In the UK, we operate night setback, while if you want to use district heating, it's better to have a sort of more continuous operation of your system. The buildings are performing poorly, mainly because it's the oldest building stock in Europe because of industrial revolution, and so the history is there's a lot of old buildings and they don't perform well, and there's also maybe a question about performance gap. So the question of low return does not exist in the UK. For example, if you take your own boiler, it's certainly a condensing boiler because that's mandatory, but most of them are installed in non-condensing mode. And the question, do you, for example, set the flow temperature on your boiler, which should be below 55. Most of the time when the boiler is installed, it's around 70. So it's nice and hot. Nobody really cares about the return and the 3% saving you could gain with the condensation. And there's also a question about design policy. In Sweden, they have limited the temperature in the 80s. So at that time in the 80s, the temperature was limited to 55 degrees. And the UK is considering similar limitation in 2021, so just now, which is very good, but that's 40 years after other countries, so lessons can be imported, but with some limitations. And the focus on the new policies is really around heat pumps and the electrification of heat. In the draft or the public or the new legislation, there's nothing much around the low return, which is a key performance indicator for district heating. So, step 2, how do Scottish public buildings perform? So every building is designed for extreme temperature, very cold. So that means that most of the season you have a mild weather, and your system would operate in part load, and that means you can reduce your temperature flow. If we look at, for example, so on left-hand side, the graph is the heating degree days calculated for the Botanic Garden in Edinburgh. And the right-hand side is the temperature flow you could use. So it's very similar to weather compensated controls. So it's a temperature flow you could drop or use depending the weather outside temperature. And the 3 lines show how much you can drop the temperature if your system is just perfectly sized, with an oversizing of 25%, which is very classic, or an oversizing of 100%, which can happen very often also. So if it's just 0% oversizing, you can reduce your temperature below 55 degrees for 146 days, or you would have to be above 446 days. If you have a little bit of oversizing or a bit more oversizing, then you can see that just existing buildings can already connect. You would just need to raise the temperature for 18 days in the winter. So the key question is, what is the degree of oversizing of your heating system? So I looked at the performance of all the building stock of the City of Edinburgh Council. So that's all the buildings. They are classified by date of build. So on the left-hand side, the old ones, on the right-hand side, the very new ones. And this shows all the blue dots, the EPC, so energy use per square meter. And as you can expect, more recent buildings are expected to use less energy. So this is energy, it's electricity and gas, so all energy. And the trend line is going down, and that's not a big surprise. What is interesting is to compare that with the true energy use. So we have the metering, electricity meters and gas meters, and we can see that the trend line is slightly going up, or is at least is flat. So there's not a massive reduction of energy use in the current building stock. And what I've done after that is compare the two. So if we compare, if we do a ratio between EPC, so expected energy use, and true energy use, we have a trend line that is going up. So that shows that it's an ongoing work. So it's preliminary results. But all buildings are more likely to be able to use reduced temperature. And so next step is to finalize those data and group that per archetype to see if we can have some specific trends. From that, I'm going to select a couple of buildings and go into a bit more detailed analysis of their energy use. So the next step, when I will have selected probably 10 buildings, is to how much oversized is the space heating system. So how do you size the system? Well, you calculate the heat demand, 100 kilowatt. You calculate, so you install your radiators, your boiler, and you have an oversizing of 0%. If you want to operate your system with intermittent night setback, you are going to oversize your radiators and distribution and boiler by 10 or 20%. Well, if you want a short preheat, you can go up to 200%. It's not recommended, but in the CIPC guidance, until a few years ago, it was allowed to go to 200%. It was possible. So you would have a heating system way oversized. And then engineers sometimes want to be a bit sure and doesn't want to make any mistakes. So there's a lot of cumulative margins, and you may end up with a system that is oversized by 400%. Currently, if a system is oversized, you wouldn't have any people calling you to complain. Maybe the system is a little bit more expensive, but you don't get that much complaints. Then the system, your building, you have calculated 100 kilowatt demand, but you may have a performance gap, and this performance gap is going to affect your oversizing. So from 400%, you may reduce that to 270. And something else is your building may have gone through retrofit history, new windows, insulation, air tightness. So your heat demand, your real heat demand is much lower. And then you may end up with an old heating system. Radiators are there, but your heat demand is very low. So you may end up with a system that is oversized by 500%. So at the end of the day, we don't really know, because each building will be different. So we can't have a trend line for archetypes, etc. So what do we do now? We look at the energy use. So that's a methodology I have proposed for that. And that's the gas consumption for a primary school in Edinburgh. And so we have a very specific pattern for the preheat time and daytime when pupils are within the school. From that, we separate daytime and preheat. So the daytime is steady state. There's no, the building is warm from 8 o'clock in the morning. From that, we do a little bit of cleaning of the data, and we have an energy signature, which is here. And from this energy signature, which is the energy use versus external temperature, we can extrapolate and know what is the energy use at design condition. We have to include some internal heat gain, etc. Eventually add 20% for night expected capacity. And we use the preheat to do a bit of cleaning to calculate the install capacity. That we have the oversizing. Once we have the oversizing, we can conclude on the temperature, the degree of reduction of the flow temperature we can achieve. One other thing is global warming. Buildings have been designed for a certain external temperature, and that's the heating degradation regarding in Edinburgh. And we can see that from the 70s, every winter, where the trend line is, we need less heat. And the projections are by 2050, there will be a significant reduction in the heating demand. And it's very similar to extreme events, because we could say there's less heat demand, but extreme events may be there, still there, even worse. That doesn't seem to be the case. So we may be able to reduce our operating temperature because there's less heat demand and our system is oversized even more in the future. And the final stage is to look at Borders College in Galashiels. And why this site? Because it's one of the first ones to operate on dual heating system. So there's a classic gas boiler, and they have installed a wastewater heat recovery system which operates at 50 degrees. So we are doing building modeling of the site, and that will be validated by empirical data to validate the model and see how the have a true case study and learn a bit more about the operation of night setbacks, etc. And that's me. Thank you. Any questions?
Thanks very much, Antoine, and thanks for your timing. Spot on. Okay, no questions coming into the forum at the moment, but one question I have, it was touched on earlier by Chris Stark, that there's been a lack of action with the built environment in terms of energy efficiency, particularly in the last sort of 10 years or so. So the difficulty to defining effective low carbon heating systems is that if we do what we're supposed to do in the next 10 years, 20 years, then our building stock is going to be very, very different if we do actually speed up our energy efficiency targets. So how does that affect? We're able to accommodate a scenario, a future low demand scenario, and then reevaluate the potential of some of these low temperature heating systems within your methodology, because the state of our building stock, if we're being optimistic, isn't a static thing. Even ignoring new build coming onto the sector, our existing building stock is if we do meet our targets, is going to be improved. So how can you accommodate that within your method?
So there's two things. Is if the heat demand is really low, there's no point to develop district heating because the heat loss would be quite high. But the thing is, if we reduce the demand, space heating demand, and the heat is provided by heat pumps, the first thing is how efficient will be the heat pump. So we have to drop the flow temperature. And even if we are able to connect, if we can drop the flow temperature further, then we would have a heat pump that is reaching 3 the COP, or even 3.5. And one key thing is, for example, if I take a big school, a district heating company will be interested if this school can connect and can supply a very low return, even lower than what is expected from a normal building. And that will help them to reduce their losses and improve their efficiency. I don't know if that answers your question.
Yeah. I mean, and clearly there's going to be a risk to the overheat, the oversizing risk that you mentioned, that risk potentially increases going forward if we do change our building stock and we find that we actually need smaller heating systems or smaller outputs of heating systems, but the bog standard heating system isn't really designed to be meeting such low heating demands.
Yeah, the question is, we are going to change the technology behind the heat we are using, so we get rid of the boiler. And so the question is, can we use a heat pump and keep the heat pump efficient for district heating and being efficient? And then if there's a program of energy efficiency that will just be rolled out over time, and as far any energy efficiency measures will improve the efficiency of the heat pump, let's say. So it can be, it doesn't have to happen at the same time.
And a question coming from Leslie: what is the age range of the buildings in your study?
The what?
What's the age range of the buildings in your study?
So most of that's roughly 300 buildings. 100 of them are schools, and I would say that it's almost 25% are pre-1919. So old historical buildings. So sort of a quarter are old ones, stone-built, sandstones, and stuff. A little bit are from the 60s, 70s, and I would say a good quarter have been built in the last 20 years. So 1 quarter before First War, 1 quarter 20 years old, and the rest is okay.
And there was a question from Bo as well about the new design or retrofit. I think you've clarified the building stock that you're looking at. A question from Tom. Interesting point you made is that where buildings have been retrofitted with better insulation, existing radiators, etc., may be oversized and so more suitable for low temperature heating. Does this mean owners like ECC, I presume that means Edinburgh City Council, should target insulation first, measure requirement, and then look at heat source?
Well, it's a difficult question. We have 2 tools in the toolbox. Should we go for energy efficiency measures or go for low carbon heat? So the answer is we need both. If the building is a listed building and an old building, it's very likely that you are not able to do much on the insulation side. So retrofit, there's a minimum retrofit, which would be change radiators, so you can drop the temperature. And then what is coming up is the way the heat is going to be charged. Just now you pay per kilowatt hour. What is happening in Sweden and Denmark, you pay for the heat you use and also for the return temperature you can provide to the system. So if your delta T between your flow and return is very small, you pay more. So if you can guarantee that you have a very low return, you have a bonus. And that's very new for the UK. And it's going to happen because otherwise the district heating, if the return temperature is too high, the efficiency of the district heating is not good. So that's a new thing coming up.
Yeah.
So
I guess with the, again, going back to the policy targets we have, it's about whole building retrofit. So actually we need to do the low carbon heating and the energy efficiency measures, and somehow we need to find a way of doing all those things together so one does inform the other. So we end up hopefully specifying low carbon heating systems for lower demand buildings, but
yes, just a quick one on the passive house. So it's a no-brainer for any new building should be passive house or equivalent to passive house, because if there is an increase in cost, it's very marginal. How high do we have to retrofit our building stock? Do we go for NRFIT, which is the passive house standard for retrofit? But it's not a marginal increase in cost. It's awfully expensive. So where do we stop? I know the council is just working with 4. They just want to experiment that and go for passive house retrofit for 4 schools and look at the numbers. And then from that, we are going to know how expensive it is, and are we going up to passive house retrofit, or where do we stop in between?
Okay, thanks very much, Antoine. And thanks to all four of our speakers. That brings us to time. Four really interesting and really quite varied presentations. It shows how large and sort of multidisciplinary this area is, and the scale of the challenge, I guess, as well. But thanks very much to all four speakers for coming along. Thanks to all the questioners and everyone who attended.